Okay, welcome to Unit 5.2. In this unit, which is divided, this video is divided into two parts, part 1 and 2, we're going to be focusing on the factors that can shift an equilibrium reaction. And I want to just sort of like pause here just to say that what you're going to learn in the next parts 1 and part 2, are not just important for passing an assessment or whatever. Chemists actually utilize this information all of the time because we want to control the reactions that we're working with, and reactions are going to tend to go towards equilibrium. We can sort of control that reaction by knowing these factors. And that may become more clearer as we go on. So, okay. In 5.1, you have sort of practiced calculating equilibrium constant, or K. In 5.2 and 5.3, you're going to actually be applying your knowledge of knowing the equilibrium constant K. And for 5.2 in this unit, what you're going to be focusing on is using the knowledge of K to predict the direction equilibrium wants the reaction wants to go into to either reach equilibrium or reestablish equilibrium. So that's what we're going to be doing here. So, well, why would a reaction want to go towards equilibrium anyway? Because we keep saying this, reactions tend towards equilibrium. Why is that? The way you should sort of envision it is the way it's envisioned in these free energy diagrams, where, let's say, for this free energy diagram here, you can see that there's free energy on the y-axis. The higher up you are, the more free energy you have. One thing that's natural, that just is a very natural phenomenon, is things tend towards a lower energy state. So let's say the ball, which represents your system, is on this upper left hill, at the top of this left hill being where the reactants are. So you have a bunch of reactants here. It's going to want to roll down until it gets to this lower energy state. Likewise, if your ball was on the top of the right hill, which is where the products are, again, it's going to want to roll down until it gets to a lower energy state. So the same reason why a ball rolls down the hill is the same reason why reactions tend toward equilibrium, because it's just a lower energy state. Now, with that being said, well, when we are dealing with a chemical reaction, we actually don't have, it's not like when you look at a reaction, you see these sort of like energy landscapes where you have hills and you have valleys, and you can say, oh, there goes the equilibrium, and this is where my ball is, and I can figure out which direction it's going to go. You don't have that information just from looking at a chemical reaction. So how can we predict the direction a reaction shift? And that's what we're going to learn about next. So predicting the direction of a reaction shift. One of the things that I used to think about when I think about shifting reaction is the electric slide, which is the precursor of the cha-cha slides and all the other slides that they have out there. And in that dance, you're sliding to the left, sliding to the right. And reactions actually do that. They're not static. They are dynamic, meaning that they're constantly moving all the time. So you can very easily sort of see reactants and products going back and forth until this equilibrium is established. Now, in order to predict which direction is going to go, whether right or left, until the equilibrium is established, you need to use what's called the reaction quotient. Because essentially what you're going to do is you're going to compare the ratio of products over reactants in your system when your system is not at equilibrium, and that's what the reaction quotient tells you, to the ratio when it's at equilibrium. And then by comparing the reaction quotient to the equilibrium constant, you can see which way it's going to shift. Okay, so couple key things to point out. K and Q are essentially the same thing, except K is at equilibrium, Q is not. It may or may not be at equilibrium. So whenever you see Q, it's like, I don't know if this is at equilibrium or not. So that's when we use Q. But if it's at equilibrium, you use K. All right, so let's try this out. In order to make that prediction, again, you need to compare Q and K. Well, first, let's try out determining Q. It's so simple to determine Q because you pretty much have already done it. It's pretty much the same thing as K, except for It's not at equilibrium. So this problem, you have this reaction here. It says a mixture of 0.1 moles of NO and 0.05 moles of H2 and 0.1 moles each of N2 and H2O is placed in a 2-liter reaction vessel at 300 K. Determine the reaction quotient. And again, this is the balanced chemical equation. There is a modification in your handout because I think I don't have this thing that I underlined here, each of N2. So it makes that modification. So with this problem, you are going to solve or determine the reaction quotient. And when I say determine the reaction quotient, I want the numerical value. So what's the value of Q? Pause the video now, and then when you press play again, I'll give you a hint if you need. Okay, so here's my first hint. Notice that they're giving you the amount of the NO, H2, N2, and H2O in moles, not in molarity, and that's what you need it to be in. So I want you to calculate the concentration of these 4 things first by taking the moles and dividing it by the volume. All right, my next hint that I have for you is that you should write out the Q expression. And the Q expression is the same as the K expression, except for it's just not at equilibrium. So it's going to be products over reactants. And so this is what your Q expression should look like. Once you have all of these values, you can simply just plug it in, and then that will give you Q. All right, so here's your answer. This is my work. This is what my work looks like, and I got Q to equal 8,000. All right, so all we've done in the CFU is just practice calculating Q. Let's move on now to using the information of Q so we can compare it to K and sort of predict the shift. All right, let's say, for example, in our first example, if Q is less than K. So you calculate your Q and then you compare it to K, and it's like, oh, my value of Q is less than K. Which direction is the reaction going to shift? In that case, you're going to shift to the right. And let me explain to you why. As you can see, both Q and K, the concentration of products are in the numerator. So that means that if K is greater than Q, that means that at equilibrium, at K, you're going to have more products than you do currently. Well, if you have more products at equilibrium, that means you want to make more products to get to equilibrium. And the only way we can make more products is for the reaction to shift to the right. So to summarize this, when Q is less than K, the concentration of products at equilibrium, or K, is greater than at non-equilibrium Q. So the reaction shifts to the right to make more products and reestablish equilibrium. Okay, so once you have all this copied down into your handout, we are going to now look at the reverse situation. Okay, so what happens when Q is greater than K? The reaction is going to do the opposite. It's going to shift to the left, shift towards making more reactants. So why is that? So when Q is greater than K, that means that the system now has more products than it does at equilibrium. So you have too many products. Okay, you want to get to that equilibrium, you have too many products to be there. So in order to get to equilibrium, you're going to have to reduce the amount of products that you have. And so in this case, when Q is greater than K, the products at equilibrium is less than that at non-equilibrium. So the reaction is going to shift to the left to consume some of those products, basically reduce the amount of products you have and reestablish equilibrium. All right, so again, take a moment to get this copied down into your notes. So with both of these examples, if you know Q and you know K, you can compare them and then determine which direction the reaction is going to shift. Now, you could utilize your understanding of the ratios and knowing, oh, my numerator products are in the numerator here. So let's say, for example, if Q is greater than K, that's the next example, my numerator for Q is bigger. So that means I have more products and I want to get rid of those products to get to equilibrium. You can do all of that which we did here. However, It may be useful for memorizing, have like a trick to memorize this, which direction it shifts depending on Q and K. And the reason why I say this, I usually don't like tricks, but sometimes, especially when you're nervous or you're taking a test, it's kind of hard for your brain to sort of process all of this sort of information. If, however, you have a trick for knowing what the answer is, then you can more easily explain your answer. So if you have a trick to know, oh, if this is greater than this, then it's going to shift this way. And now you can back it up with the reasoning, because you definitely need to have the reasoning. You have to be able to explain why for the AP exam and also for college exams. So what's a trick for memorizing the direction of the shift? First thing you're going to do is alphabetize Q and K. So if you write Q and K in alphabetical order, K is going to go first and then goes Q. And just write them next to each other. Second thing is you're going to put in your equilibrium symbol. So remember with the equilibrium symbol, the mouth is going to face what's ever larger. So let's say we're in a situation where K is greater than Q. Our value for K is greater than Q. So I'm going to have my mouth facing the K. Then finally, the last thing we're going to do is we're going to use this equilibrium symbol to make a shift arrow. So what do I mean by that? This equilibrium symbol kind of looks like an arrowhead. So we're just basically going to take that symbol and turn it into an arrowhead. And so the direction that this arrow is pointing is to the right. So when K is greater than Q, the reaction shifts to the right. We can do the sort of the same thing. In this case, let's say it's the opposite, where Q is greater than K. So again, we put in our equilibrium symbol, and then we turn that into an arrowhead. And when we do that, it's pointing to the left, so the reaction shifts to the left. So again, this trick is just for memorizing. You might want to note that in your packet. It's just for memorizing. It will not help you to explain it. So you can't explain it by saying, oh, the equilibrium symbol is telling me why. No, you have to explain it using the notes that you saw previously. All right, so with that being said, now that we know that by comparing Q and K, we can determine the direction that the reaction is going to shift, you're going to try this CFU. So take a moment, pause the video now, and then if necessary, I will give you some hints. Okay, so you're asked to predict the direction of the reaction proceeds given these amounts of HI, H2, and I2. So once again, you want to calculate the concentrations of everything because they give it to you in moles, not in molarity. So you need to do that first. Then you want to write an expression for Q, which is, products of reactants, and then plug in the values that you got for these concentrations into your Q expression to calculate Q. Finally, once you have Q, they give you K. They tell you that the K for the reaction is 50.5, so you can compare the value of K with that of Q, and then based on which one's bigger, you can determine which direction it shifts. All right, pause the video now, and when you press play again, the answer will be revealed. Okay, so here is my work for it, so you can take a look at it. I didn't show the work for calculating the concentrations of HI, H2, and I2, but here are the values. This is my expression for Q, and then I plug that stuff in, and then the reaction is going to shift to the right because K is greater than Q. All right, so now we're ready for part 2. So that's it for this video. Hope you found it helpful.